you very much. I'm going to use this. Is this okay? Yes. So, yeah, thank you. Thank you to the committee for reading my thesis. And of course, I'm very honored to receive this award. And I'm grateful for the opportunity to talk to you about this. So, my thesis was in the area of optimal classical planning. So we're looking at single agent and discrete problems there, kind of simple problems within planning, and we're trying to solve them optimally. And what we are doing there is to use A-star search with an admissible heuristic, so a lower bounding heuristic. And my thesis makes 3 contributions in this direction. So there's an extension to an existing heuristic combination technique called cost partitioning, and 2 new heuristic families called operator counting and potential heuristics. I'm going to talk about all 3 of these, but in the end I would like to manage to talk a bit about the connections between these ideas, because I think they are the most interesting part of it. So let's start with cost partitioning. So cost partitioning is the answer to the question, or one answer to the question, how we can combine admissible heuristic estimates. So admissible heuristics are lower bounds, so we could maximize over them and still have a lower bound, but the maximum is only as good as one of the individual heuristics. Ideally, we would like to sum them up, but that's not admissible anymore, and cost partitioning is a way to make them additive so we can actually sum them up. So let me show you an example. So this is a binary counter. It counts from 0 to 3, and there are 2 operators, the red one and the blue one. And we can get heuristics from that task by projecting it to one of the variables. So on the top we project to the first variable, and on the left we project to the second variable. And then as you can see in both of these abstractions, the cost to reach the goal is 1. So from each of them we get a heuristic estimate of 1, but we can't just add them up because that would be inadmissible. So cost partitioning allows us to split the cost of the blue operator so it's only counted in the top abstraction, and split the cost of the red operator so it's only counted in the left abstraction. And then we can add them up and get the heuristic value of 2. So the extension that I did for this was an observation that we don't have to restrict these costs to be non-negative. We can allow negative costs. So let's start with the same task and the same projections. This is actually the best you can do with non-negative costs. But if we also allow negative costs, we can use the cost of -1 for the blue operator on the left side and increase the cost of the blue operator in the top abstraction by 1. And this sums to a heuristic value of 3, which is perfect in this case. So this seems like a minor change, but it actually, oh sorry, I wanted to say one more thing, because this might seem like cheating to you. So it might seem like we can just keep increasing the value in the top abstraction, and but if we just lower the value on the other abstraction enough. Yeah. So we can do that. If we increase the value to 3, we have to decrease it to -2 in the other abstraction. But then the top abstraction indeed has a value of 3, but the left abstraction now has a cycle with negative cost, which means we can reach the goal with cost that is as low as we want by just repeating the cycle more and more often. So in this case, the cost in the left abstraction is -infinity, and in total, this is a valid way of splitting up the cost. It's just not a very good one, because it leads to a heuristic value of -infinity. And it's actually possible to compute the best possible way of splitting up the costs in time that is polynomial in the size of these abstractions. And in practice, this makes a huge difference. So this is, these are heuristic values of some tasks. And as you probably know, just a small increase in a heuristic value will often reduce the search space a lot. So a large increase in heuristic value, like we see here, is very useful. Okay, so that's it for the first part of this thesis. The second part is operator counting. And the main idea of operator counting heuristics is that you look at the space of all plans, but you ignore the order. So you have elements in here that represent sets of plans that all use the same number of operators. For example, the lowest one over there represents all plans that use the red operator 3 times, the blue operator once, and don't use the brown operator at all. Now if we have some properties of plans, for example that we need to use the brown operator at least once, as we would get from a landmark, or that the blue and red operator together cost 4, which we might get from a projection, or that the red operator has to be used exactly once more than the brown operator, which we might get from flow balance constraints, then we can restrict the set of possible plans. So every plan has to satisfy all of these conditions. So that means that every plan has to lie in this intersection of all of these constraints. But with this technique, we are not looking for an actual plan, we are looking for a lower bounding heuristic. So if we pick the cheapest element within the set and compute its cost, then this gives us a lower bound on the actual planning cost. And this is neat in theory because we can actually express many of the existing heuristics in this framework, and that means that we also can combine them easily, because every heuristic that we can express in this framework just gives us one more constraint that we can add to this linear program, and adding multiple constraints to the linear program just combines the strengths of all of them. It also allows to reason about the heuristics that we express in this framework more easily, because they are all expressed with linear constraints, and they are all expressed in the same language, so it's easier to compare them and analyze if one of them dominates the other one. And finally, these heuristics are what we call declarative, which means that instead of spending a lot of time coming up with a good idea for a new heuristic, you can write down information that you know about the problem in a declarative way and let the LP solver do the hard work of figuring out how to combine this information and coming up with a good heuristic value. And finally, in practice, this gives state-of-the-art heuristic quality if you choose the right set of constraints. And the reason why it can come up with such good quality, or one of the reasons, is that there are synergies between these constraints. So a landmark constraint can interact with a constraint that comes from a state balance condition, and they can strengthen each other. Okay, I'll come to the last part of this thesis, which is about potential heuristics. And a potential heuristic is just the mathematical form of a certain set of functions. So these functions are defined over a set of features that can be present in a state or not, and associated weights for these features. And the value of the function is just the weighted sum, so the sum of the weights for all features that are true in the state. So an example is in chess, where you would have a weight of 1 for each of your own pawns that is still in the game, and a weight of -1 for each of the opponent's pawns that is still in the game. And then if you want to evaluate the material value of a position, you just add up all of the weights of the features that are in this current position. Okay, so the nice thing about expressing heuristics like this is that it's possible to treat heuristic design, so the problem of coming up with a good heuristic itself, as an optimization problem. And here's one example of how we did this. We specified features first, and in our case we looked at features that talk about at most k variables in the problem. And then we declaratively again specify what properties we want the heuristic to have. So in this case, we are using this heuristic for optimal search, so we would like them to be admissible and consistent. So we were able to come up with linear constraints that completely characterize the set of admissible and consistent potential heuristics with a certain set of features. And since these are all linear constraints, we can also define a quality measure that tells us what it means for a heuristic to be good. And if this is also a linear equation over these weights, as for example the average value or high initial value or high value in a certain set of sample states, then we can use an LP solver to optimize these weights under the conditions that the heuristics have to be admissible and consistent. And this gives us the best possible potential heuristics among the set, because the constraints characterize all admissible and consistent potential heuristics. If we maximize some property, we will get the best one among all of them. Okay, finally, to come to the connections between these ideas, I think the main theorem of this thesis is that combining operator counting heuristics, so I talked about how you can combine them by just using different constraints and putting them into one linear program. And solving this linear program is one. Combining operator counting heuristics in this way is equivalent to computing the optimal general cost partitioning of these heuristics. So the cost partitioning where negative costs are allowed. And this is interesting because it allows us to interpret heuristics. We can interpret heuristics as cost partitioning, or we can combine heuristics in new ways. So for example, we can combine heuristics in a way that is stronger than the optimal cost partition. And we have a similar results for potential heuristics, which I'm just going to gloss over here, but potential heuristics can also be understood as general cost partitionings of some heuristics. There are a bit more details that I'm leaving out here, but in essence they can be seen as a dual view on cost partitioning or on operator counting heuristics. Okay, so the main parts of this that I would like you to take home from this talk is that there are three things that are extended cost partitioning, operator counting heuristics, and potential heuristics. And while they look different and they have different ideas behind them, they are all very closely related to each other. And the nice thing about this close relation is that it allows us to transfer results. For example, we can transfer complexity results between the different ideas. It allows us to combine heuristics in new and stronger ways, so even better than the optimal cost partitioning. And finally, it helps to understand the heuristics better, to understand what they are doing, what they are actually computing. So with that, I would like to thank, first of all, my advisor, Malte Helmert, my reviewers, Chris Beck and Sylvie Thibault, all of my co-authors, and everyone in Basel, all of my colleagues in Basel, and of course, all of you guys for listening to me. Thank you.
We've got a couple minutes for questions.
Okay. So we have questions, but I don't see anything. Yes.
What happens when you have time?
Sorry?
What happens when you have time?
So I think in the operator counting framework, adding time would be an interesting way. So there's one set of heuristics, the delete relaxation heuristics, that can be expressed as operator counting heuristics, and they use some variables that specify the first time an operator is used. And having these variables is fine if you can share these variables between different operator counting constraints, as long as they have the same semantics in each operator counting constraints. So one of the things that makes these operator counting constraints fast to compute is that they ignore the order of operators. So adding everything you know about time might make it as slow as planning itself, but adding some information about time in a way that is shared across these variables, shared across different constraints, I think that would be interesting.